So hello, welcome back. All right, so last time we were talking about pop stack sorting. I had the hats, Rice Krispies. There are more Rice Krispies if anyone wants them. So they're not. So if you want to just come up or something, they're here. Right. So I said if L is a locally finite meet semi-lattice, we can define this map pop from L to L, and it's defined by just sending an element x to. Essentially, it's just taking it to the meet of the elements covered by x, although I have to add this little x here just in case x is like the bottom element, because then it doesn't cover anything, and I want to not take the meet of the empty set. So here I have this example where I said, okay, here's a lattice. And I said, so pop sends this top element down here, and it sends this element here, and sends this element here. This one goes to the bottom, these two go here, and then the bottom is fixed. And I guess the other thing I did last class was I finished proving that the weak order on a finite Coxeter group is a meet semi-lattice. It's actually a complete meet semi-lattice, but I didn't prove that, although I think this is proven in the book. So in particular, we can define pop on a Coxeter group. And I was also talking about what's called the Coxeter number of a Coxeter group. So this is like a special number associated to the group that appears in a lot of places. So let me remind you what that is. So suppose W is finite, then the Coxeter number of W is just 2 times the number of reflections in W divided by the number of simple reflections. And we said as an example, I should say this is usually denoted by H. So when W is Sn, we said H is 2 times, well, the number of reflections is n choose 2, and the number of simple reflections is n minus 1, and this simplifies to just n, so the Coxeter number of Sn is just n. So actually, let me tell you what all the Coxeter numbers are, because we have a characterization of finite irreducible Coxeter groups, so I can tell you what their Coxeter numbers are. So here's W, and here's the Coxeter number H. So if we take A n minus 1, which is the same as the symmetric group Sn, as I just said, the Coxeter number is n. We could also take Bn, the hyperoctahedral group, and the Coxeter number here is 2n. We could take Dn. The Coxeter number for that is 2n minus 2. Then we have E6, E7, and E8. Let me just make sure I get their numbers right. So they are 12, 18, and 30. Then there's F4, H3, H4. Their Coxeter numbers are 12, 10, and 30. And then we have the dihedral group, I sub 2 of m. And, well, actually, we can figure out very easily what this is. So I don't know if I've said this, but the number of reflections in the dihedral group of order 2m is just m, like half of the elements are reflections. And then the number of simple reflections is 2, so this should just be 2 times m divided by 2, so we get m. So I mentioned last time there was this theorem of Unger from 1982, which said that like if you take the weak order on the symmetric group, the maximum number of steps needed to sort a permutation is n minus 1. And so here's a theorem that I proved, which is generalizing this to Coxeter groups. So the maximum number of iterations of pop needed to send an element of my finite, let's say W is a finite irreducible Coxeter group. The maximum number of iterations needed to send an element of this to the identity, which is the bottom element of the weak order. And here I'm defining pop by letting L be the weak order, is the Coxeter number minus 1. So in the case of the symmetric group, this is what Unger proved because it was n minus 1, but in general it's the Coxeter number minus 1. And then also, if J is the set of all simple reflections minus some single simple reflection S, so for some little s, then this actually attains the maximum. So, well, sorry, not this actually. It's the element W naught of J times W naught. So you take the long element of the parabolic subgroup generated by J times the long element of the entire group, and this requires H minus 1 iterations of pop to reach the identity. So I can give an example with like the dihedral group. So here's like, if I took I2 of, I don't know, 5, for example. So the weak order looks like this. And if I do pop, the top element goes straight to the bottom because I'm taking the meat of these two elements, and that's just the bottom, like the greatest lower bound. And then the bottom element also gets fixed by this. And every other element kind of just goes down one step. So this element goes here, this one goes here, this one goes here, this one goes here. So here it's very easy to check the statement because, well, the maximum number of steps needed is like one of these elements. It would take 1, 2, 3, 4 steps, which is 4 is 5 minus 1, and 5 is the Coxeter number. Okay. Yes, Yinzo.
So why is this useful in general? Why was it defined in the first place?
Why is what?
Why was the Coxeter number defined in the first place?
Oh, why is the Coxeter number? Okay, so it appears in various places. For example, I'll define something called a Coxeter element. So the word Coxeter shows up everywhere. There's something called a Coxeter element, which is basically where you multiply all of the simple reflections together in some order. These turn out to have nice properties, and they're studied for various reasons. And the order of a Coxeter element, like the order as an element of the group, turns out to be the Coxeter number. So that's like one place where it shows up. But yeah. Okay. So I think this is essentially what I wanted to cover from chapter 3. I think there's other stuff in chapter 3 that deals with like poset topology, but I don't really want to talk about poset topology here. So before starting chapter 4, I thought maybe I'd just like say a bunch of other random things and tell you about like other combinatorial objects, because I guess like this is supposed to be, you know, combinatoric, so maybe it's good to, you know, discuss other combinatorial objects. Oh, and also chapter 4 will be about a geometric way of thinking about a Coxeter group. And so maybe to like set that up and just sort of gently introduce this idea, I'll talk about this geometric way of thinking about the symmetric group. So, if I take 1 less than or equal to I, less than j, less than or equal to n, I want to let h sub I j be this hyperplane in Rn. So it's going to be the set of all the vectors in Rn such that the ith and jth coordinates are equal. Xi equals xj. Okay, so this is some codimension 1 subspace. It's a hyperplane. And this collection of hyperplanes, so the collection of hyperplanes Hij for all I and j is called the braid arrangement. Or I guess I could call it like the nth braid arrangement, because there's one for each n. But I'll just call it the braid arrangement. And what you can do is you can reflect through one of these hyperplanes. You can consider the linear transformation that just reflects through this hyperplane. And that has the effect of swapping the ith and jth coordinates. So reflecting through the hyperplane Hij has the effect of swapping the ith and jth coordinates. So the symmetric group Sn is going to act on Rn by basically permuting coordinates. Okay. So Sn acts on Rn by permuting coordinates. And I guess the way I would write this is, if I have some permutation w, and I want it to act on a vector x1 through xn, I would just get x sub w inverse of 1. And I want to use inverses so that this becomes a left action. So you can check that you have to have inverses here to make it work. Through x sub w inverse of n. So what this means is that we can identify Sn with the subgroup, the group generated by these reflections through the hyperplanes in the braid arrangement. So Sn can be identified with the group generated by reflections through hyperplanes in the braid arrangement. says say more. I wrote in my notes, say more. I don't know what I want to say. Okay, what else can I say? Oh, here's something I can say. So maybe let me draw a picture of what this looks like in n equals 3. So if n equals 3, we're looking at 3-dimensional Euclidean space, and we're cutting it with 3 hyperplanes. But I don't want to draw a picture in 3 dimensions, so what I'm going to do is observe that these 3 hyperplanes will all contain the line, which is the span of the all ones vector. So what I mean by this is, take all of the points whose coordinates are all equal, right, in Rn. This is some line, like it's the points of the form xxx. And that line will be contained in any one of these hyperplanes, because this hyperplane is just saying, the ith and the jth coordinates are equal, so if all of the coordinates are equal, it's going to be equal, contained in all of these hyperplanes. So the picture that you should have in your head is like you've got these 3 2-dimensional planes that all intersect along this line, but I can kind of quotient out by that line, essentially is what I'm doing. Or you could sort of imagine like taking a hyperplane orthogonal to that line and looking at how that intersects the 3 braid arrangement hyperplanes that I care about. And if you do this, you end up getting a picture that looks like this. So you get 3 lines. So really each one of these lines should be representing like, I guess you can imagine it like coming out of the blackboard. So this line is actually like a plane that comes out like this, and this line is a plane, and this line is a plane. But I'm just drawing like the intersection of these 3 planes with the blackboard. And so this will break up our space into 6 regions. And these 6 regions correspond to the 6 elements of S3. And one way you can see this correspondence is basically like if I take some point which is not in, so by region I mean like, if you deleted these lines, then the connected components of the complement are these 6 regions. And if I pick some point, let's say I take some point that's like, I don't know, 1.3, -2, and 8, or something like that. Well, I know that the coordinates are all distinct because this does not lie on one of the hyperplanes. And so I can consider like the relative order of these points, or of these coordinates. And that's essentially giving me a permutation. So that's how these regions correspond to permutations. So I might have like 1, 2, 3, and I guess, okay, I think I want to do the left weak order here. Because I'm swapping, so okay, let's do this. Let's say this is the hyperplane H1, 2. So if I reflect through H1, 2, then I want to be did I get this wrong? Maybe I did this wrong. I'm mixing up left and right something. Okay, maybe I just won't label the regions. There are 6 regions and they correspond to permutations. And actually like, this should be the weak order. And I think I want it to be the left weak order. I think I want it to be like 1, 2, 3, and 2, 1, 3, 1, 3, 2. This should be 3, 1, 2. This should be 2, 3, 1, 3, 2, 1. Okay. Actually, another thing I can say is that what I've drawn here is a hexagon, which is like a 2-dimensional polytope. And you can do this for higher dimensions as well. So you can say, if I go into like n equals 4, then I'd have like a 3-dimensional picture after I mod out by the span of the all ones vector. And then if you take like the convex hull of these points that are like representing like these permutations. So I could think of this as like the point 1, 2, 3. I could think of this as the point 2, 1, 3. This is the point 1, 3, 2, and so on. And if I take the convex hull of these points, I get some polytope. This is called the permutahedron, and it's very interesting. It has cool properties. maybe at some point I'll say more about the permutahedron. Okay. So let me talk about set partitions, and that'll relate to the braid arrangement. So a set partition, this is like a classical kind of combinatorial object that people will study. So a set partition of a set of integers from 1 to n is well, it's basically a way of partitioning the set into disjoint subsets whose union is all of bracket n. So it's a collection, maybe I should say it's an unordered collection of subsets, disjoint subsets, of bracket n, whose union is bracket n. So here's an example. Let's say n equals 6. I could take the set partition, okay, let's do like 1, 2, 5. So this will be one of our subsets. And then another one might be like 3 and 6. And then maybe the last one is just 4 by itself. So set partitions can show up in various places. Right, so actually, okay, so I didn't plan this, but like last class I talked about pop stack sorting. And then yesterday in the Open Neighborhood seminar I talked about stack sorting. And now I can tell you about a different variant of stack sorting. So this came about because my friend Noah like texted me about a year ago and said like, oh, like what if you had, okay, so let me get my socks. So what if, you had a bunch of socks and they were like arranged, you take them out of the wash and they're like arranged in some order like this. Okay, so here are my socks, white, white. I have this Christmas sock here, and then I have my yellow sock, and then I have my white sock again, and then I have a Christmas sock. Okay, so I have my 6 socks. And so you can think of this as a set partition, right? This is corresponding to this set partition that I wrote here, basically where like 2 numbers lie in the same block of the partition if the socks in those positions have the same color. Right, so I would have like 1, 2, and 5, 3 and 6, and 4. And so he said, okay, like here's this problem. You take your socks out of the wash and you want to sort them. So you want to like sort them into some order so that all of the socks of the same color are right next to each other. So like maybe I would want all of the white socks next to each other. I would want my 2 Christmas socks next to each other, and I'd want the yellow socks somewhere. And it could be like, I could do this. Or, I could also do this, that would also be fine. So I have some, I want to sort them like this. And he said, I wonder if you can do like stack sorting for set partitions, where basically you take a stack and you put your socks into the stack, so you can put 1 sock into the stack, put another sock into the stack. So last time I drew a stack, which was a pop stack, and it had like a spring at the bottom, which like popped everything out. But this is not going to be a pop stack, this is just a stack, which means that like you're able to pop one thing at a time out of the stack. So you can put your socks into the stack and take them out. This would not be like an actually efficient way of sorting the socks, but this was just sort of a mathematical curiosity. And he said, I wonder if there's like a way to do stack sorting for set partitions. And I said, okay, yeah, like this could work, but you should not be calling it a stack. You should be calling it a foot, because what you're really doing is you're taking your sock and you're putting it on your foot, and then you have another sock and you put it on top of that, And then like whenever you want to take a sock off of your foot, you take off like the last sock that you put on. So like the data structure of a foot is really like the same as like the data structure of a stack, except it's a foot. So anyway, we wrote a paper called Foot Sorting for Socks, which is basically stack sorting for set partitions. I don't know if I'll go into it, but yeah, so we submitted this to a journal, and we got 2 referee reports. One of them was positive and said like, oh, this sounds really cool, and this is fun. And the other one said something like, so they weren't as positive, and they said some readers might be off-put by seeing real human feet in a math paper. So like I had a bunch of pictures of like my feet, and I was putting socks on my feet. And you can find it online, but
it's linked in the notes.
It's linked in the notes. Okay, cool. Yeah, so it's linked in the notes. Yeah, so anyway, we submitted somewhere else. But, okay. Yes, Yunzo.
What is the name of Noah's mom?
What is the name of Noah's mom?
Melissa.
Thank you. I didn't know that. What? Why?
Cool.
Okay. Interesting. Okay. I'm glad someone knew that. Okay, so we have set partitions. So why am I talking about set partitions other than the socks? Well, you can think of these actually as, well actually, okay, before I get to how to think of them in terms of the braid arrangement, let me tell you some other places where you can, or some other things about set partitions. So the number, so this is just some combinatorics. The number of set partitions is called the nth Bell number. So the number of set partitions of bracket n is called the nth Bell number. So I think oftentimes it's denoted by B sub n, but I don't want to use B sub n because I use that for the hyperoctahedral group, like over there. So let me call it Bell sub n. Maybe it's not clear that that's a subscript. So there are like cool things that you can do with the Bell numbers. Here's one fact that's nice. It's just like the generating function for them. So if you take the sum, do I want to go from 0? Yeah, I want to do in at least 0. I guess the assumption is that like the 0th Bell number is 1, so there's like one set partition of the empty set, which is just nothing. So the sum overall in at least 0 of, you take the nth Bell number times x to the n over n factorial. So this is called an exponential generating function. It's where you take your sequence that you care about and you just like sum over that sequence times x to the n over n factorial. And in this case, it has a nice formula, which is that it's e to the power of x minus 1. So I won't prove this, but this is just a cool fact. Here's another place where set partitions come up. So you can think of it as like the number of rhyme schemes of a poem of a given size. So like, so Bell sub n is the number of rhyme schemes of poem with n lines. So like if I had a poem where the rhyme scheme was like, you write it as like A, B, A, something like this. This would just correspond to a set partition where I have 1, 2, and 4. And then 3 is by itself. Maybe I can do this in color. A, A, A. And the B is 3. Okay, so how does this relate to the braid arrangement? Well, set partitions of bracket n correspond to intersections of hyperplanes in the braid arrangement. What I mean by this is you intersect some of the hyperplanes in the braid arrangement. This gives you some set, which is like a subspace. And the possible subspaces that can arise by intersecting hyperplanes in the braid arrangement correspond to set partitions. So here's an example with, or I guess we can do maybe this example here with n equals 6. So n equals 6. Let's take the set partition 1 to, I think I said 1 to 5, yeah. And then 3 and 6, and then 4. So basically what I want to do is say that because 1 and 2 are in the same block of my partition, I want to use the hyperplane h sub 1, 2. And I want to intersect that. Well, 1 and 5 are also in the same block, so I want to intersect this with h sub 1, 5. Now, I'm also going to intersect it with h sub 2, 5, but this is actually not needed, because what am I doing when I intersect h1, 2 and h1, 5? I'm saying I'm looking at the set of points where the first and second coordinates are equal. And here I'm looking at the set of points where the first and fifth coordinates are equal. So if I intersect them, this is giving me the set of points where the first, second, and fifth coordinates are all equal. But then I don't really have to intersect with h sub 2, 5, because that's just telling me now that I want the second and fifth coordinates to be equal. But if I already know that the first and second coordinates are the same, and I know that the first and fifth coordinates are the same, that implies that the second and fifth coordinates are the same. But I also want to intersect this with h sub 3, 6, because 3 and 6 are in the same block. And like if I write this out in terms of coordinates, this is literally just the set of points x1 through x, well, okay, it's the set of points of the form x, x, y, z, x, y, such that x, y, and z are real. And so you can see this corresponds to the set partition. Okay. So one thing that's nice about this point of view is that we'll talk about later the fact that, well, let me focus on finite irreducible Coxeter groups, but later actually we'll talk about a geometric way of thinking about any Coxeter group. But for now, let's just say we have a finite irreducible Coxeter group. There is sort of an analog of the braid arrangement. It's called the Coxeter arrangement of the Coxeter group. And it's again going to be some collection of hyperplanes in Euclidean space with similar properties here. Basically, you can reflect through those hyperplanes. And when you look at the group generated by those reflections through those hyperplanes, that ends up being isomorphic to the Coxeter group that you care about. So you can then kind of identify your Coxeter group with the group generated by those reflections, just like how I did here, saying the symmetric group can be identified with the group generated by the reflections through the hyperplanes in the braid arrangement. And so what this means is that we can get an analog of set partitions for any finite irreducible Coxeter group by just intersecting hyperplanes in the Coxeter arrangement. So, yeah, I guess I'll just say intersections of hyperplanes in the what's called the Coxeter arrangement of a finite irreducible Coxeter group W are, I guess, analogs. Maybe I don't need quotes. Are analogs of set partitions. So this is like another example where we can take some combinatorial objects, which are like set partitions, and say, oh, here's a way of viewing them, in this case in a geometric way, and then this geometric formulation generalizes to other finite irreducible Coxeter groups. I don't actually know how to do foot sorting for other Coxeter groups, though. I think I'm kind of using the fact that there are like actual numbers here, which correspond to the positions of the socks. And I don't really see a good way to do that if you take other, like an arbitrary finite irreducible Coxeter group, like in a sort of uniform way. Maybe you could do something for like the hyperoctahedral group where you have like sine socks or something. Maybe they're like some are inside out or something, but yeah. Okay. Any questions up to here? Okay, let me also just mention, here's a fact. So intersections, yeah. Intersections of hyperplanes in the Coxeter arrangement also correspond to, I'm going to say, conjugates of parabolic subgroups. Okay, so there's sort of different uses of terminology in the literature. So sometimes people will talk about a standard parabolic subgroup. This is what I've been referring to when I say take a subset J of the set of simple reflections, I guess like here. And then there's this standard parabolic subgroup, which is just the subgroup generated by J. And sometimes people will say that a parabolic subgroup is just some subgroup that is conjugate to a standard parabolic subgroup. I guess here I'm writing out explicitly, it's like a conjugate of a standard parabolic subgroup, or just, okay, parabolic subgroup. But anyway, the way that this correspondence works is, so again, W will act on Rn. And this is just because it's, you can identify W with the subgroup generated, or the group that's generated by the reflections through the hyperplanes in the Coxeter arrangement. And if U is some conjugate of a standard parabolic subgroup, so let's say it's like W inverse capital WJ W. Maybe I want the inverse on the other side. I don't know if it matters. Then, so the points in Rn that are fixed by the elements of U form an intersection of hyperplanes in the Coxeter arrangement. So the points in Rn fixed by all elements of U form an intersection of hyperplanes in the Coxeter arrangement. And this is a one-to-one correspondence. So basically, if you have an intersection of hyperplanes in the Coxeter arrangement, you can say, what are the elements of my group that fix that set of points? That will actually be one of these, I guess, non-standard parabolic subgroups. In other words, something like this. And then on the other hand, if I'm given this subgroup, then I can look at the things fixed by it, and that forms an intersection of these hyperplanes. Okay. So, okay, maybe I can do an example in the case of S6. If I took this intersection of hyperplanes, the elements of the symmetric group that are fixed by this, or sorry, that fix this, would be the permutations that permute 1, 2, and 5, and like permute 3 and 6. Okay, and that's some conjugate of a standard parabolic subgroup. Okay, any questions? Okay, so we can also think about set partitions as forming a poset. Actually, it'll be a lattice. So let me talk about this. So let me write capital pi sub n for the set of set partitions of bracket n. And I want to put a partial order on this. This is called the reverse refinement order. And it's defined by saying, so put a partial order. A partial order on pi sub n by, I'll just say such that a set partition rho is less than or equal to a set partition rho prime if every block, so again, the disjoint subsets in the set partition are called the blocks of the set partition. I don't know if I mentioned that. So if every block of rho is contained in a block of rho prime. Okay. Yes, Yunza.
Sorry, so did you define Coxeter arrangement?
I haven't defined the Coxeter arrangement. I'll do this, I think, in chapter 4, in like when we start that. But it's It's just a fact that like there is a way to define this arrangement so that it has these properties. But like in chapter 4, I think this is done for like any Coxeter group that's not necessarily finite. Things get weird though because like here I'm talking about reflections. Things are nice when you have a finite irreducible Coxeter group because the reflections are sort of what you think of as like reflections in a Euclidean space. In more generality, you have to define a bilinear form on the space, and the reflections are defined with respect to this bilinear form. And then things can get weird because like you might not have a Euclidean metric. You might get like a hyperbolic space or something. Okay. So this is the nth partition lattice, and it is a lattice. So let me draw an example of this. So for n equals 5, there are, or no, not 5, I want to do n equals 3. There are 5 set partitions. Maybe instead of drawing them with like a bunch of curly braces, let me represent them like this. So the bottom one will be 1, 2, 3, and so this is my notation for the set partition where I just have 3 singleton blocks. So there's 1, and then there's 2, and then there's 3. And another one will be, I'll have 1, 2, bar 3, so this would be where 1 and 2 are in the same block, and 3 is by itself. And then there's also the one where 1 and 3 are in the same block, and 2 is by itself. And then there's the one where 2 and 3 are in the same block, and 1 is by itself. And then finally there's the one where just 1, 2, and 3 are all in the same block. And this is above all of these. Okay. Maybe it's more helpful if I use red. So this is a lattice, and that's not too hard to check. Basically, the meet operation is like the greatest common refinement, and the join should be where you just sort of, well, you combine blocks like as minimally as you can. Okay. Any questions up to here? Okay, so another thing I can tell you about are Coxeter elements. So I mentioned this before, actually, with respect to the Coxeter number. So, okay, here. So in the same way that there's a distinction between standard parabolic subgroups and parabolic subgroups, which are conjugates of them. So maybe I should have called this a standard parabolic subgroup. And a conjugate of a standard parabolic subgroup is just a parabolic subgroup. There's also a notion of a standard Coxeter element. So a standard Coxeter element, or sometimes I'll just call it a Coxeter element. So maybe I'll put standard in parentheses of my Coxeter group W is just an element obtained by multiplying all of the simple reflections together in some order. So is an element, often it's denoted by C, and it's obtained by multiplying all of the simple reflections in some order. So here's an example in Sn. So there are many Coxeter elements that I could choose in Sn, but maybe the simplest one is where I just, yes,
Sorry, I don't know if you said this, but the partition lattice is always not distributive.
it's always not distributive? Is that what you asked?
Yeah.
So I guess, okay, it will be distributive if n equals 1, or if n equals 2, but I think beyond that it is not distributive. Yeah. Yeah, so this is not distributive. Right.
Because I guess we can take, just like generalizing that, 1 through n minus 1, and then n is the set.
Yeah.
And then one where you flip n and n minus 1, and then they have the same joint and the same heap, but they're different. Or they're different.
Yeah, I mean, one way you could see it is that this is not distributive, which you could check just directly, and this will sit inside of any bigger partition lattice. Like if I kind of just take the bigger partitions and ignore the numbers, 4 through n, this will sit inside of it. Okay, yeah. So here's an example in Sn of a Coxeter element. I could just take C to be S1, S2, Sn minus 1. This is sort of the most naive way that you could write down an ordering of the simple reflections. And if you multiply this out, well, let me write what this is in cycle notation. So where does 1 go? If I multiply, and I multiply from right to left, so the 1 gets fixed by this, and it's not touched by any of these except for the S1, which sends it to 2. So 1 gets sent to 2. And then the 2 doesn't get touched by any of these except for S2, which sends it to 3. And then S1 does not touch 3. So 2 goes to 3. And if you just keep doing this, you'll find that 3 goes to 4, and so on. And eventually this goes to n. And n goes back to 1 because, well, Sn minus 1 will send n to n minus 1. And then Sn minus 2 will send n minus 1 to n minus 2. And it just kind of goes down the line until eventually S1 sends 2 to 1, so n goes to 1. So this is like the long cycle here. This is a standard Coxeter element. But there are other examples. Actually, here's a nice other example of a standard Coxeter element. You could say, let me multiply all of the simple reflections with odd indices, and then I'll multiply all of the ones with even indices. So another is, maybe I'll call this C prime. This would be where you take, so I guess it's the product over I odd of Si. And then you take the product over I even of Si. Now, I guess one thing I should point out is that when I write this product, I'm thinking of multiplying all of these simple reflections together in some order, but it doesn't actually matter the order that I choose because all of the odd index simple reflections commute with each other. So I can multiply, if I had like S1, S3, and S5, I could do S1 times S3 times S5, or I could do S5 times S1 times S3, and it's going to be the same thing because all of these commute with each other. And same for the even ones. So actually, this is a special example of a more general thing you can do for any finite irreducible Coxeter group. Because if you remember from the classification of finite irreducible Coxeter groups, the Coxeter diagram is a tree. In all of the cases, it's always like there are no cycles. I mean, you sort of prove this, or most of this in like a p-set problem. And so you can choose a bipartition of this tree. Basically, you choose like two sets, x and y, of vertices, so that none of the vertices from x are adjacent to each other, and none of the vertices in y are adjacent to each other. And then you can say, I'm going to multiply all of the simple reflections from x, and then all of the simple reflections from y. So like in the case of Sn, like if I had, okay, this is like A6, which is S7. What I'm doing is I'm saying, okay, I'm going to color these red, and then I'll color these yellow. And all I'm doing when I take this product is I'm saying multiply the red simple reflections and then multiply the yellow simple reflections. But like, this is kind of a nice thing to do because this works for any finite irreducible Coxeter group. Yes?
So are they all different?
Or what all different?
So I guess, like, the ways of, if you arrange the simple reflections in different ways.
So they're not all different. They will be the same if and only if, well, okay, so like you can do commutation moves, right? Like this basically goes back to Matsumoto's theorem, which says that like, so this will be a reduced word, always. And you can get from this reduced word to any other reduced word by doing braid moves and commutation moves. But you're never going to do like a long braid move because you don't have multiple copies of any letter. So the only moves that you can actually do are the commutation moves. And so like in this case, well, you know, I could have written this as like S1, S3, dot, 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 or I could have written it as like S3, S1, dot, dot, dot. They're going to give me the same thing because S1 and S3 commute.
Oh, okay. So what's the number of?
So the number of them will be the number of acyclic orientations of the Coxeter graph, actually.
Which is?
Well, in this, so in the case of Sn, it will be 2 to the n minus 2. So we have a path with n minus 2 edges. So this is like S7, right? This is S7. There are 5 edges, and I can orient them, each one of them in any way. And essentially, the way you get the orientation is you say, let's say I have, okay, S2 here and S3.
Like for every connected pair, either S2 on the left or S3.
Right. Yeah, so you say if S2 comes before S3 in my ordering, then I'll draw an arrow this way. If S3 comes first, then I'll draw it the other way. And if you do this for all of the pairs, you get some orientation that looks like this. Chris, did you have a question?
Yeah, I was just wondering, you have to do each of the simple reflections once.
Yes, exactly once, right. Yeah. Yeah, so this is kind of a nice way of thinking about the Coxeter elements. They correspond to acyclic. So what I mean by an acyclic orientation is it's a way of orienting the edges of the Coxeter graph so that you don't have any directed cycles. And you don't want a directed cycle because you don't want to say like S1 appears before S3, S3 appears before S4, and S4 appears before S1, because then like that doesn't make sense. Okay, so actually here's an exercise that will be on the p-set that I'll release today.
Oh, Paul.
Yes?
Also, I guess, because there's no cycle, there's no, like, ordering that, I guess, like, contradicts itself, kind of?
Yeah, I mean, that's essentially, yeah, what you want,
Okay.
why you want it to be acyclic. Yeah.
Okay.
I mean, this doesn't matter in the case of like Sn or anywhere where you have a tree because there are no cycles anyway, so there's no way you're going to get a cycle. But if you had a Coxeter graph with cycles, you don't want to have directed cycles. So this is an exercise that will be on the p-set. So suppose the Coxeter graph of W is a tree. So this is the case if we have a finite irreducible Coxeter group, or you can have some infinite Coxeter group that also just has a Coxeter graph, which is a tree. Show that all standard Coxeter elements are conjugate to each other. So in particular, this is true if the Coxeter graph, or if the Coxeter group is finite and irreducible. So if W is finite and irreducible, I guess this is true even if it's not irreducible, then you have a forest and it's still true, but let's just assume irreducible. Then all Coxeter elements are conjugate to each other. And so in particular, they all have the same order in the group, right? So I mean like the group theoretic order where it's like the minimum power such that the element to that power is the identity. So they all have the same order. And a fact is that this order is the Coxeter number, so I mentioned this earlier, is the Coxeter number H. So I had this table before of these special numbers, and like one of the reasons that they're important is that because they are the orders of Coxeter elements. So for example, in Sn, the order of this element, this is an in cycle, so its order is in, and in is the order of, or in is the Coxeter element, or Coxeter number. Sorry. Okay. Any questions up to here? Yes, Insa.
So, are there cases where T and S are both infinite, but like there's some like bijection between those two sets and the ratios?
Oh, I think no. Well, I mean, okay. I guess if they're both infinite, then like there should be a bijection. But I usually think of the Coxeter number of an infinite Coxeter group as being like infinity. And this makes sense here because actually the order, so if you're in an infinite group, the order of a Coxeter element will actually be infinite.
Okay.
This will always be true. So it does make sense in this setting to say that the Coxeter number should be infinity, like if you think of it in this way. Yeah, that's a good question. And okay, so this is a standard Coxeter element, but let me just define, so a Coxeter element. So maybe I shouldn't use the parentheses here. Maybe I should actually call this a standard Coxeter element, and a Coxeter element is just something that is conjugate to a standard Coxeter element. Conjugate so in fact, in Sn, the Coxeter elements like in this definition, will just be all of the in cycles. Just all of the elements that you can get by cycling through the numbers in one big cycle. Yes?
So let's say, like, is it then all like standard Coxeter elements are conjugate to each other? Is it
So for this,
for
Oh.
the group below.
so I mean, okay, it is true that all of the, well, okay, this is true, but also all of the standards are conjugate to each other. Yeah, so yeah, maybe I should also just say all standard. But what I wrote is also true if I take this definition, because if all of the standard Coxeter elements are conjugate to each other, then by conjugating them, I get a bigger set, which is still all conjugate to each other. Okay? But yeah, I guess like in terms of the logical flow of the board, I should not have written this before this if I wanted to omit the word standard. Okay. Okay, so let me define another partial order on, or maybe I don't know if I want to get that far. Okay, I'll do what I can, and then we'll talk about the absolute order next time. But yeah, maybe I have time. Okay. So remember, T, like capital T, is the set of reflections. So I'll just remind you, T is just the set of WS, W inverse, such that W is in W, and S is in S. And I want to let L sub T of W, this is like the length with respect to the reflections. This is the minimum number of reflections. Needed to write W. So what am I saying here? Well, typically we've been thinking of the Coxeter group as being generated by the simple reflections. So when we talk about the length of an element, we say what is the minimum number of simple reflections needed to express our element. But the group is also generated by the set of all reflections. And so you could similarly say, well, what if I asked for the minimum number of just reflections, not necessarily simple, needed to represent my element of the group? And this sort of leads to what's called like a dual way of thinking about the Coxeter group, where you kind of replace the simple reflections by all of the reflections. Right. So let me give an example for SN. So for W and SN, the reflection length, that's what this is called, of W is just n minus the number of cycles in W. Right, so for example, like the reflection length of the identity, well, this should just be 0, but this is because it's n minus, well, the number of cycles is n because really the identity has just a bunch of singleton cycles. So it's n minus n, which is 0. And then similarly, if I take the length, the reflection length of a transposition, ij, well, this should be 1 because I can write it as just itself. That is an expression for ij as a product of reflections. And this is n minus n minus 1 because my transposition has a single 2 cycle and then it has n minus 2 singleton cycles. So it has n minus 1 cycles total. So this is 1. So I started working with this guy, Nathan Williams, that I told you about, because after I wrote my paper, Pop Stack Sorting for Coxeter Groups, he said, oh, well, what if you do like a dual version of this where you like look at, your Coxeter group is generated by the reflections and you can define some like dual way of doing it. I don't think I'll talk about that here, but he suggested that we call this pop stack torsing because you replace the S's with the T's, like you switch the roles of S and T. So it's like instead of stack sorting, it's stack torsing. But yeah, so anyway, that is a weird name. But okay, I guess I only have a few minutes left, so I don't think I'll define, maybe I can define the absolute order, but here, let me just note something. So if U and V are conjugate, then the reflection lengths are the same. This is because if you write U as a product of reflections, then you can just conjugate each of those reflections by whatever the element is you need to conjugate from U to V, and then that'll give you an expression. Like when you conjugate a reflection, you get another reflection. So then that'll give you an expression for V as a product of reflections. And so now I can define this absolute order. So the absolute order so this is like the third partial order that we're talking about on a Coxeter group. We've talked about the strong Gruhal order, we've talked about the weak order, and now there's the absolute order on W is defined so that U is less than or equal to V. Let me maybe write less than sub ab for the absolute order. This is if and only if the reflection length of U inverse V is the reflection length of V minus the reflection length of U. And you might recognize that this looks a lot similar to the definition of the weak order. This basically is the definition of the weak order if I replaced reflection length by just regular length. Okay, so I think I'll say more about the weak or the absolute order next time, but that's at least the definition. So yeah, I think that's all for today. There are still Rice Krispies.